Right, so now let's look at converting between different number bases. So avoiding base 10. So we want to go directly from like octal to hexadecimal, for example. Right? And you can sort of go the long way around and convert things from the base that you're given into base 10, and then from base 10 into others. Actually, here we're starting with the base 2 number, and we want to convert it first to octal and then hexadecimal. Okay, but tables like this are very useful. Okay, so here we're given like decimal, hexadecimal, octal, and binary of the digits from 0 to 15. So we're looking from 0 to 15 because we want to be able to use the hexadecimal. Okay, so that kind of covers whole range from binary to hexadecimal here. All right, so basically, whichever number bases I'm looking between, then I can use the conversion. All right, so let's say I want to use, I'm going to start with 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, and I know this is in base 2. Okay, we're given that that's in base 2. All right, so I want to convert it to octal. Okay, now I noticed that my octal base system only uses numbers 0 to 7. Okay, all right. So these 10 to 17 can occur in octal, but they're not the correct coefficients. The coefficients that you get in octal have to be less than 8. Okay, and if I look in the binary row, I can see that if I'm converting the digits 0 to 7, the binary will only go up to 3-digit numbers. If you go to 4-digit numbers, that's basically jumps up to that's going to be 8. The number 8 is 1, 0, 0, 0 in binary. Okay, so that's why I've gone too far. All right. So what we want to do if we want to go from binary to octal is we want to start on the right and form groups of 3 digits. So I have 3 digits, 3 digits, 3 digits, 3 digits, and however many digits we have there. So each of these groups get transformed into an octal digit. Okay, so if I look at 1, 0, 0 on the chart, that corresponds to a 4 in the octal row. And 1, 1, 1 corresponds to a 7. 0, 1, 0 is this one, corresponds to a 2. Another 1, 1, 1, which is a 7. And a 1, 1 is a 3. Okay? So here's the octal representation. All right, so just with that chart right there, it's fairly straightforward to do it. All right, now let's do the same binary number, but change it to hexadecimal. So let me copy it down. So I have 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, base 2. All right, so for the hexadecimal, okay, we see that if I want to cover the full range of hexadecimal, then in the binary row, my binary representation of these numbers goes up to 4-digit numbers. Okay, the next one, if I kind of want to go to notes, the next one is going to be 5 digits, but for hexadecimal, I need my binary to be in groups of 4. Okay, so you go through your binary starting on the right and group it in groups of 4. Last one can be anything, okay, up to 4. Okay, so we look at each groups and convert them. Okay, so 1, 1, 0, 0 in the chart is a C. 1, 0, 1, 1 in the chart is a B. 1110 is a E. And 11 is a 3. Okay, so 3EBC is the base 16 conversion there. Okay, so that's sort of to avoid going to base 10. So let's not go to base 10 and then to base 16 or base 8. We can sort of go directly between those using the charts. All right. All right, let's do a couple more examples like this. Okay, so let's find the binary expansion of 7, 6, 5, base 8. Okay, so now we're looking at the row in base 8 and changing all these numbers into groups up to 3 digits. Okay, so if I look at 7 in my octal, that changes into 111. And 6 changes into 110. And 5 changes into 101. So that's the base 2 representation. All right, and then for A8D in hexadecimal, can we go to the chart? So A corresponds to 1010. 8 corresponds to 1000, and D corresponds to 1101. So that's the transformation to base 2. Okay, it's basically just kind of copying numbers, but that's a kind of quick conversion chart. All right, so let's look at adding and subtracting. So we're looking. Oh, not adding and multiplying, okay? So in different number bases. Okay, so first the addition algorithm. Again, sort of the steps are here, but I'm just going to demonstrate by example. Okay, so I have these two numbers. I have A is 1110 base 2, and I want to add it to 1011 in base 2. And basically this is just like addition in base 10, but you can't go over, you can't use any digits other than 0 and 1. So if you are going over, you're going to find the mod, okay? And basically the mod goes as the answer, the remainder of the division goes as the answer, and then you carry. So you're going to carry to the next place value. Okay, so for example, 1 plus 0 is 1. Well, that's fine. Okay, but now 1 plus 1 equals 2. Can't write 2 because it's not allowed to use. But you say, well, 2 mod 2 is 0. Right, so I divide 2 by 2. I get a remainder of 0, which goes here. And the whole number of the division gets carried. Okay, then again I get 1 plus 1 is 2. Okay, so if I divide 2 by 2, I get a mod of 0, remainder of 0, and the whole number carries. Then 1 plus 1 plus 1 is 3. So I have 3 mod 2, the remainder is 1, and the whole number, 3 divided by 2 gives you 1. The whole number carries over to the end. Okay, so here's the answer to the addition there. Okay. All right, so multiplication. So the multiplication algorithm is very similar to doing in base 10. So let's multiply. Okay, so first you kind of take the unit digit. Okay, so this is the digit that multiplies to the 0, and we multiply it with the top number. So 1 times 0 is 0, 1 times 1 is 1, 1 times 1 is 1. And now this 0 belongs to 2 to the power 1. So we move it a space inward. We're going to put the answer starting under this one because we're at a different place value, okay? So 0 times 0 is 0, 0 times 1 is 0, 0 times 1 is 0, okay? And then I'm going to multiply by 1. Again, we indented another space because this 1 is the coefficient of 2 to the 2. So we got to start our answer here because these belong to the 2 to the 2 power. So 1 times 0 is 0, 1 times 1 is 1, 1 times 1 is 1. So just like the division in base 10, with those indents because you're going to a different place value. And then we add. So we use the addition algorithm. So we get a 0. 1 plus 0 is 1. This is 1. This is 1. And this is 1. Okay, so again, this answer is in base 2. Okay, cool. All right. We actually do an extra example that's in a different number base, so you can see how it works outside the base 2. Okay, so let's say I have 1, 2, 7, 4 in base 8, and 3, 4, 6 in base 8, and I want to add them. Okay, so 1, 2, 7, 4 plus 3, 4, 6. Okay, so I get 6 plus 4 is 10. But 10 is not allowed in base 8. So 10 divided by 8 is 1 with the remainder of 2. Okay, so the whole number carries over and the remainder gets put as the answer. Okay, then I have 4 plus 7 is 11 plus 1 is 12. 12 divided by 8 is a 1 with the remainder of 4. All right, 3 plus 2 is 5, and then another extra 1 is 6. So just a 6 with no carryover, and then a 1 here. Okay, so this is the answer in mod 8. All right, let's do a multiplication. Let's say I have 546 mod 8 times 124 mod 8. Okay, so let's have 546 times 124. Okay, so I do 4 times 6 is 24. And I have to do 24 divided by 8 is going to be 3 times with the remainder of 0. I do 4 times 4 is 16 plus 3 is 19. 19 divided by 8 is going to be twice with the remainder of 3. 4 times 5 is 20, plus 2 is 22. All right, so 22 divided by 8 goes twice with the remainder of 4. Good. Okay, so now we're going to go to this 2, and we indented. So we're going to start writing our answer here. So 2 times 6 is 12. 12 divided by 8 goes once with the remainder of 4. 2 times 4 is 8 plus 1 is 9, which goes in once with the remainder of 1. 2 times 5 is 10, and 11 divided by 8 is going to go once with the remainder of 3. Okay, let's do this last one. 1 times 6 is 6, 1 times 4 is 4, 1 times 5 is 5. Now we need to add these up. Okay, so I get a 0, and I get a 7, and then I get 11. 11 divided by 8 is once with the remainder of, what's this? With the remainder of 5. Okay, and then I have 7 and 3 is 10, so it goes in once with the remainder of 2, and then this is a 7. Okay, so this is the base 8 representation here. Okay, so that's how it worked in another number base. All right, so now let's look at the modular exponentiation. All right, so raising something to exponent. So this is probably the more difficult ones, but also the kind of more useful ones in terms of computers. Okay. So again, sort of just like raising a number to an exponent for computers is not very efficient. It kind of takes a lot of computation and space. Okay. So again, we're not talking about small numbers like this. We're talking about, basically when computers work with exponentiation, basically it's necessary to do computing with huge numbers. Basically, we're raising big primes to big primes when you're doing cryptography. So people don't break your passwords, don't break the codes. So these are like simpler examples, but it's not very efficient to just do it straight, okay, repeated multiplication. So we want to use a more efficient algorithm. So the algorithm that's presented here, basically you're going to take the exponent and write it in binary notation. So we're going to take that exponent of 11 and write the binary expansion of that, okay? Then we're going to break up the 3 to the 11 into these parts. Okay, so basically with this binary expansion 1, 0, 1, 1, that means I have an 8 because this is 2 to the power 3. I don't have a 4, I have a 2, and I have a 1. Okay, all right, so that's what makes up 11. So in binary, 11 is made by 8 and 2 and 1. Okay, so we write that out. Okay. All right, so basically we're going to find 3 to the 2 is 9, 3 to the 4 is 9 squared, 3 to the 8 is 81 squared, and so on. So basically this process of squaring and squaring and squaring again is much more efficient for the computer to do. Okay, so once we square everything, then 3 to the 11 is going to be, as I said, 3 to the 8 times 3 to the 2 times 3 to the 1. But from the repeating squaring, 3 to the 8 is 6, 5, 6, 1. And 3 to the 2 is 9. And 3 to the 1 is 3. And then you multiply those numbers to give you 177, 147. All right? So again, this is more efficient for a computer to do than raising 3 to the 11th power, just like by multiplying 3 by itself 11 times. All right. Okay, so let me walk you through this example now. Okay, so this is mostly what computer use this for. So it's not just sort of raising things to exponents, but finding the remainder, finding the mod of something raised to an exponent. Again, we're basically in the next couple of sections, we're going to see how this is useful. So again, sort of all these things, this arithmetic, this modular algebra is part of something bigger, okay? So we want to find 3 to the power 644 mod 645. So you can see that we're getting to big numbers or bigger numbers here. So just in the last example, we first want to expand 644. We want to expand the exponent in binary. So if you do the expansion of 644 in binary, we get this. And then we kind of identify, let's see which powers we have in our binary expansion. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we see that the non-zero ones are 2 to the 9, which is 512, to the 7, which is 128, and 2 to the 2, which is 4. So we write 644 in powers of 2. So 644 is 512 plus 128 plus 4. So we break up this exponent into these 3 different parts. Okay, so those are the only non-zero powers of 2 present in 644. Okay, and now we're basically going to do repeated division. We're going to repeatedly find remainders. Okay, so we start at 3 to the 2, and we do 3 to the 2 mod 645. Okay, so 3 to the 2 is 9. 9 mod 645 is 9, because we're saying what's the remainder if I divide 9 by 645. So we're going to get 0 with the remainder of 9. All right, then we're going to go to double the power. 3 to the 4 mod 645. Okay, so I know 3 to the 4 is 81. 81 mod 645 is the remainder is just 81, because again I get 0 with the remainder of 81. Now 3 to the 8. Okay, so 3 to the 8 is 81 times 81 mod 65. And now we're going to use one of those rules that we learned in the last section. Right, so if I have a product, I can expand this out as 81 mod 65, 81 mod 65 mod 65. Okay, so this is not really that useful because I get a remainder of 81 in each of them. So I actually do have to multiply it out. So 6561 mod 645 is going to give you a remainder of 111. All right, next step, I need 316. So I take that as 3 to the 8, 3 to the 8 mod 645. Again, I use that expansion formula that I have. 3 to the 8 mod 645, 3 to the 8 mod 645, mod 645. And now this becomes useful because from the previous step, I know that 3 to the 8 mod 65 is 111. So I replace it in both cases. I multiply these out. I get 12321. I find the remainder of 66. So we're repeating the process. So 3 to the 32. I break it up into 2 3/16s. I use that expansion formula. I know that the remainder for doing the division is 66. I multiply them together. I find the remainder is 486. And I go to 364, break it up into 3 to the 32s. I plug in that 486. I multiply it, I find the remainder 126. So you kind of basically keep repeating the process until I get to the 3 to the 512, because that's the biggest power of 3 I get there. So that you can see that that's why I need these to be powers of 2, because we're doubling each time. All right, so now we put everything together. Okay, so we see that to expand 3 to the 644, I need the 512, the 128, and the 4. So I go into this list right here, and I see that 315 mod 645 is 111. And 3 to the 128 mod 645 is the 396. And the 3 to the 4 mod 645 is the 81. So I put all these together. We multiply them out, and we find the remainder is 36. Okay, so you can't do this in your calculator. If you plug in 3 to the power 644, the calculator breaks. Okay, and even if you sort of plug it in the computer, it's too big for the computer to handle. All right, so that's that computation. It's not really possible to do this exponent the regular way. But if you're just trying to find the remainder of this exponent to this mod, then this is sort of a process that you can program into your computer to find the remainder. All right, so, okay, so that's the last part of this section, this modular exponentiation.